This is too big. Today we're going to. There we go. Let's do the schedule, and we'll start with that, and then we'll take a look at some reactions of alcohols. So today. We'll finish up with alcohols. We'll talk about their reactions. And so our next exam is the 29th. 11/29, which is after Thanksgiving, right? So we have, that's next Monday. Oh, apparently I'm streaming the wrong thing. What? That's weird. Why did the title come up that way? Okay, well, whatever. Who cares? We're going to have our exam 4 on the 29th. And so what I thought is going to be the best solution for this, because we have our final on the 6th. What we'll do there is technically one more chapter we have to do. It's on ethers and epoxides. Which is really not very interesting. We'll see that what I'm going to do for that is, because I've my OChem 2 class this semester at the other college, they start this semester with ethers and epoxides. So I have videos from earlier this semester. I'm just going to give those to y'all so you can use them as the ether. So we're not going to necessarily stream them. I'm just going to give you the videos. So that way we'll have more time for review. So today we're going to finish our reactions of alcohols. I'm going to also put up the videos for your ethers and epoxides. There's not too much going on there. Ethers and epoxides and sulfides are pretty boring. But we'll see. There's also going to be some good naming practice in that. And some good just sort of synthesis. So it'll be good for you. And then so you'll watch I think it's either 2 or 3 videos. On ethers, epoxides, and sulfides. And that means that on Wednesday we can review, if we are so inclined. We can choose a time to do that. If the this 10:45 time doesn't work for us. So whoever is interested in attending a review on Wednesday, just post it in Discord. Say like, hey, can we do it on Wednesday at 3 p.m.? And I'll be like, sure, sounds good. And so we'll try and figure out the best time based on that. So we can alter the time, but we'll do it on Wednesday. All right. So it can't be from between 9:10 and 10:35, or we'll say after 6 p.m. So anywhere kind of within that, so between 10:35 and 6 p.m., let me know a good hour and a half for us to review. All right, and then so we'll have on the 29th will be your 4th exam. On the 1st, we'll have another review. Also time. And then we can do the one on the 3rd as well. So we'll look at those. So does this seem okay as our schedule for the last couple of weeks here? And I realize, it's going to be whoever is happy or lucky enough to be watching these to get this information in time. But that's okay. So, alrighty. Well, in that case, we'll go ahead, if there's no questions here or anything, we'll go ahead and take a look at our last reactions of alcohols here. So, couple things we can do with alcohols. We can do a substitution or elimination, or we can oxidize them. And when you watch the videos on ethers and epoxides, you can see them acting as nucleophiles. So, if we want to talk about substitution and elimination of alcohols, let's start with elimination, because this is what we've studied before. If we needed to remove an alcohol, if we wanted to eliminate it, we could use Shane's favorite reagents, sulfuric acid, concentrated. Remember, this is on page 326 or whatever, as we saw. And then that's going to need some heat, and then we end up with the eliminated product here. And if we wanted to do, this is an E1 type of elimination. If we wanted to do an E2 type of elimination, we would need to first tosylate it, and then we would go ahead and put in our base of choice. Maybe it's potassium T-butoxide and a polar aprotic solvent like acetone. Although that's probably not the best. Whatever, it works. With some heat, and then we'll end up doing an E2 elimination here. Onto our alkene. So we can form an alkene by eliminating an alcohol, either using concentrated sulfuric acid, or you can tosylate and eliminate E2 style. All right, so either way works. With substituting them, we have a couple of ways. We could tosylate, make that OH into a leaving group, and then we can put in some sort of nucleophile. And that would be an SN2 type process, where we would then have our nucleophile replace the tosylate. So we can do that with iodine, with chlorine, with a cyanide, whatever. For example, yeah, we could do that. So tosylation, you need the tosyl chloride and pyridine. You can put in a nucleophile like cyanide, and we can use acetone here. And we will end up having our new nucleophile present on this. So that works. However, we're going to see that there's two new ways to substitute that OH away. And we're going to see that we can convert it directly to a chlorine by using thionyl chloride and pyridine. Pyridine is just going to be there to help get rid of the extra chloride at the end. So we do need a base here. Thionyl chloride is this guy. Which is SOCl2. It's used to turn alcohols into chlorides. And what's interesting is, although this is not chiral, we end up with the same stereochemistry. So if this was on a wedge before you use your thionyl chloride, you'll end up with your chlorine also on a wedge. So if you start with a wedge, you end with a wedge. And how this will work, if we look at the mechanism for this, we're going to have our alcohol attack. Alcohols are weakly nucleophilic, right? So that goes in and attacks. I'm going to keep this on the wedge. So we will have now our oxygen. We're going to have our base come along and deprotonate this thing. This can happen as the first step. Either way, it's okay. Your base is going to come in and deprotonate. Pyridine is a pretty weak base. I should use the blues. Oh. Let me redraw this one in blacks just so we're super clear about what's what. Okay, so we're going to have our pyridine come and grab our proton. And so we are left now with the O directly bonded to the sulfur. Oops. That sulfur carbonyl or sulfonyl is going to go ahead and close back down, and it's going to kick out a chlorine. In this process, by the way, we've lost the pyridinium. And here we lose the chloride. Now, this here is a fantastic leaving group. We have a great leaving group now. So, what's going to happen is the chlorine here is going to do some interesting stuff. It's going to go ahead and come in and attack. We're going to end up making a new double bond and kicking out. I'm going to just get rid of that. Our sulfur bit there. And we're going to end up now having our chlorine here, and we will lose SO2 gas and another chloride. So another chloride will be lost, and we're going to have our SO2 also go away. And the reason that this works out so well, because SO2 is a gas, this just bubbles away and drives forward the reaction through it's going to get it away, push the equilibrium forward, right? So we are going to remove a product from our situation here, and we're going to end up having this come in. So this, as posited, this mechanism will end up giving us the dash chlorine though, right? I don't know if you've noticed that. This would technically give us the dash one. And so it turns out there is some evidence to suggest that this is not what's going to happen here. Because that would give us the dash, because we're going to have an SN2 type. We're going to kick out our sulfur-containing bit there. The reason that this is probably an unlikely mechanism is because pyridinium and chloride go together very, very well. We're going to see that this thing is very, very happy to just precipitate out of solution. So we're not going to really have the chloride in there to remove it in the first place. And so what we consider might happen then is, if we take a look at that part here, we're going to see that we might end up instead having this happen intramolecularly, where we have the thionyl chloride comes in and simply replaces the oxygen in one step, giving us our same configuration as before, also losing the SO2. And so we kind of have this transition state. It's a four-membered transition state here, where we have a bond forming between the chlorine and the carbon that had the oxygen. And then the oxygen bond is breaking, CO bond is breaking, forming this S double bond O, which will bubble away, giving us the same configuration. So we're going to see here that because this thing is super stable, that pyridinium is going to grab that chloride right away. And so it's not going to necessarily be available to act as a nucleophile. That's why we use pyridine often with things containing chlorine as a leaving group, is because pyridine is exceptionally good at getting rid of chlorine. It gets it out of the equation. So it's no longer here to bother us. So it's unfortunately not going to be as simple as just chlorine coming in like that. So in reality, we'll probably have something more similar to having the chlorine come around and globbing back on directly. All right, so if we kind of just want to look at the transition state here a little bit. I'm going to just draw this other stuff. We're going to see the bond beginning to form there and beginning to form there. And we're kind of breaking. We're going to be breaking these two bonds, forming the new one. So those dotted blue ones are forming, the purple ones are breaking, and so as a result we end up with the retention of configuration by using thionyl chloride on an alcohol. So suffice it to say that with the help of the pyridine there, we're going to end up getting the retention of our configuration. All right, note that if we use tosylation, notice we use the pyridine there as well to get rid of that chloride, so we don't have that attack. However, now we're going to go ahead and throw in some chloride anyway in a second step. In this case, we get the inversion of stereochemistry. So this retains the same stereochemistry, this one inverts it. So same alcohol, will give you different products in different ways. So if you tosylate, you end up tosylate and then substitute, you get the inversion. If you go ahead and use the thionyl chloride and pyridine, you're going to end up with the inversion here. Alrighty. There's a couple other reagents we can use to do this. We can use PCl5 would work. If you use phosphorus pentachloride, you get the inverted stereocenter. If you use PBr3, you can get the inverted stereocenter. Either way. The thionyl chloride generally will retain your stereocenter, but the others will invert it. And with the phosphorus, it's very similar to the mechanism of how we'll just do it. Let's use a PBr3. So oxygen attacks like before, kicks out a bromine. So we'll have our bit here. And because we don't have a base here in this set of conditions, this is why we're going to get the inversion. What's going to happen is our bromide now, because it's not being abstracted by a pyridine like the chloride was with the thionyl chloride, you end up kicking this out, yielding SN2 style, the brominated substrate. And you end up losing your, I don't know, some sort of phosphorus-based acid there with some bromines. So again, this bit here is a good leaving group. And it's able to leave, and so you have your bromine coming in from the backside, doing a backside attack onto it, and you'll get that. All right. So, cool. That's kind of it for substitutions. So you can do all sorts of fun things. So if you wanted to, say for example, do something like this. Well, we have some options here. We're going to need to substitute this in, but maybe we can't do it directly. The only thing that retains stereochemistry is thionyl chloride. And that's not being done here because this is not a chlorine. However, we know, remember, always look at the product when you're looking at how to synthesize something. If we look at the product, how do we make this thing? Well, this would be using a nucleophile like the sodium methyl sulfide and a polar aprotic solvent like acetonitrile. We would just need some leaving group, right? Do an SN2 on that. And so then we need to think, okay, how are we going to get from the alcohol to this bromine? It could be chlorine also, it doesn't matter. some leaving group. I chose bromine because we very often do, right? To do this, we would just need PBr3. That's all we need to do. And so this reaction would be 2 steps. It would be first step PBr3, second step the SN2 with our sodium methyl sulfide. And so notice we invert the stereochemistry, then we invert it again, giving us overall the same stereochemistry that we started with. So you can exploit this as much as you want. You can take your alcohol and convert it to an alkyl halide, and then do all your SN2 reactions, SN1, E1s, E2s, whatever you like. It's just a way of interconverting functional groups. All right, so fun stuff there. Any questions so far on this substitution stuff? Or the eliminations, I suppose. All right. Then let's look at oxidations. We're going to see that alcohols can be oxidized to either aldehydes or ketones. Aldehydes can be oxidized further into carboxylic acids. So if we take a secondary alcohol and oxidize it, we get a ketone. If we take a primary alcohol and oxidize it, we get an aldehyde. And then we can oxidize an aldehyde further to a carboxylic acid. So those are options. A tertiary alcohol, of course, we can not oxidize it. No way we can make that to happen. In order to oxidize something, we need a CH bond. So remember, oxidation means either increasing the number of bonds to oxygen or decreasing to hydrogen. In order for an oxidation to happen, if you have no CH bonds to lose, you can't oxidize something. So we can talk about some of the common ways to do this. We can take common oxidants I'm going to separate these into strong and mild oxidants, and we'll see that there will potentially be a difference. So strong oxidants are we have the chromate plus sulfuric acid, or even acetic acid. This gives us chromic acid. We can see that if we take a dichromate, we also get chromic acid. So chromic acid is a strong oxidizing agent. KMNO4 is a strong oxidizing agent. And nitric acid is also a strong oxidizing agent. So these are kind of the big three, big strong oxidants: KMNO4, chromic acid, or nitric acid. All of these are strong oxidants. So these will all work out very strongly. We're going to see that mild oxidants are going to be a bit more complicated, and we'll see why in just a little bit. We're going to have PCC, which is Pyridinium Chlorochromate. Which is a mixture of pyridine, HCl, and CrO3, chromium 6 oxide. This is all the same thing. We have the Swern oxidation, which uses oxalyl chloride, dimethyl sulfoxide. We're going to look at the mechanisms for these. And then triethylamine. Well, let's try this again. There we go. So first up, oxalyl chloride, and then DMSO, and then triethylamine. And then the last one is desmartin periodinane. And we'll take a look at that one as well. So we have kind of three ways of doing strong oxidation, and then we have three ways of doing mild oxidation. And the difference between the two sets of reagents is strong ones will take a primary alcohol to a carboxylic acid. And they'll take a secondary alcohol to a ketone. Your mild ones, though, will take a primary one to an aldehyde and a secondary one to a ketone. So your ketone is going to be formed either way from a secondary alcohol. But a primary alcohol will yield different products depending if you do a strong oxidation or a mild oxidation. And so the reason that we are interested in these mild ones is because sometimes we want an aldehyde instead of a carboxylic acid. If we want a ketone, who cares? Do whichever one. Doesn't matter. But if we want an aldehyde, we have to have specifically something that will oxidize the alcohol to the aldehyde, but will not oxidize the aldehyde to the carboxylic acid. And so that's the difference here. So it's important that we have these sorts of things here. All right. So if we want to think about how these reactions are happening, we'll see that we'll use the one of these sets of reagents. So mild ones, PCC, Swern, or desmartin periodinane, which is also abbreviated DMP. We'll look at them each. So the pyridinium chlorochromate, what happens here is that's only 5 bonds. There's a 6th one. With the chlorochromate, you have this plus the pyridine, which is going to be in the form of the pyridinium ion. So you've got a positive and a negative thing there. What happens is you're going to end up kicking out your chlorine, and you're going to end up taking that and let's just take a look. So we might describe it instead putting a negative charge on the chromium here. Let's take an alcohol. Going to pop this open. We may close down to kick out the chlorine. We end up opening this up. That's got an H, sorry. Let's pour chromium Has 15 different things on it. What's going to happen here is we have a proton shift happening. We can have that abstract the proton. And then we can have really any sort of base at all. It can be another molecule of the pyridine. It can be maybe even a chloride here, because this is a fantastic leaving group. We can have a chloride come around, or a water or something else, something like that is going to come and grab our proton, kicking out our chromium, which is going to then kick out the chlorine. So we end up regenerating our chloride here. And so that's the HCl part, right? The HCl comes in there, and then we end up oxidizing our species here. We end up making essentially the chromic acid. And we will regenerate our Cl. All right, and we've got our lone pair there. So with this, we can end up getting our lovely ketone out, or aldehyde if that's what we used. So we don't oxidize further. With the Swern oxidation, that one's a little bit more complex of a mechanism. You don't really need to worry about the chromium-based oxidations. That one is not typically a mechanism that we're going to force you to learn. However, this one is one that we do force you to learn. Make sure to learn the mechanism. So remember, for Swern conditions, we have oxalochloride. Oops. And DMSO. Those are the first step, and then the second step, we have the triethylamine. And it's going to take either a primary alcohol, make it an aldehyde, or it's going to take a secondary alcohol and turn it into a ketone. So first step for Swern actually does not involve the alcohol at all. We just need the oxalochloride and the DMSO to do their thing. So oxalochloride looks like this. And then DMSO, of course, is the following. So what's interesting about DMSO is its resonance form. Often actually exists. This is actually pretty stable, having the O- and the S+. This is called a Zwitter ion. It's got both positive and negative. It does exist in that Zwitter ionic form actually predominantly. It does prefer to have the positive and negative, simply because the oxygen is so much more electronegative than the sulfur, and the sulfur is relatively polarizable. The oxygen can really grab its electrons, and so we often see it drawn as the following. And so we're going to use that in our mechanism. So here we go. We're going to go ahead and attack one of these carbonyls and open it up, thereby giving us the following. So we'll just have open that up. We still have our positive charge on the sulfur. We now have our negative charge up here on what used to be the carbonyl. Carbonyl is going to close back down, kick out the chlorine. Now leaving us with the following. So we have this molecule now. Chlorine is going to come, chloride rather, is going to come and attack the positive sulfur. And here's the really interesting part. So we end up, we're going to end up making a whole bunch of gases here, just like before. Once that chloride attacks, we're going to form CO2, carbon monoxide, and another chloride. We're going to see that getting rid of all this stuff is that going to be positive? Yes. So we're going to end up with our sulfur species here. So with this, we're also going to have CO2, CO, and another chloride. So we've ended up kicking out quite a few things here. So with this, here's where the interesting part happens. So this is these reagents were there to set up this species. This is our reactive bit. Because now we can take our alcohol and it is going to attack the positive sulfur. Kicking out the chlorine. All right, so we lose another chloride. We now have our alcohol attached there. We have our base. Comes in and deprotonates. So we'll lose our base there. And I'm going to actually write out these methyl groups because this is where the interesting stuff happens. So this is perhaps the weirdest part of the mechanism. Is what actually happens is we're not going to eliminate this. We're going to see that another molecule of our base is actually going to deprotonate this and leave it as a carbanion. As always, someone is outside maybe causing all sorts of ruckus. Okay, so with this, I'm kind of drawing it somewhat terribly because of the terrible artist that I am. I'm going to just switch these if that's okay with everybody. It'll be a little bit easier if I show it this way. That can just rotate, right? It just rotates, no problem. This is where the actual oxidation happens. This one is going to grab our proton next to the alcohol. That's going to form our double bond, and it's going to bump the electrons from the oxygen and sulfur onto the sulfur itself. In both cases, of course, the sulfur is positive. And what's interesting here is we lose dimethyl sulfide. terribly stinky, very, very stinky compound. But we end up with our alcohol, or aldehyde now. So we will have oxidized this to the aldehyde, and we've ended up with quite a few side products. We've got CO2, we've got CO, carbon dioxide, carbon monoxide, 2 chlorides, which are going to end up being having fun with some triethylammoniums. So those chlorides get globbed up there, and we also lose DMS, which is another gas. So we produce 3 gases in this, as well as 2 solids, and yielding our aldehyde. So this reaction is very efficient. Producing gases is always a good thing because equilibrium drives it away. If we precipitate something out, equilibrium drives it forward, right? We're eliminating products in both cases. Eliminating products pushes your reaction forward, the Chatelier's principle. And so as a result, we end up oxidizing this. And so we will get an aldehyde only. This does not oxidize further to the carboxylic acid. And so as a result here, we're going to end up with our product of interest. All right. Any questions on that one? So lots of side products there. We have another one with relatively low atom economy, which is the Des-Martin periodinane. DMP. I have to look at this one because I can never remember the entire molecule. So DMP is, I'll draw them as double bonds. We have an iodine here. And we have this thing oxidized like crazy. We have an oxygen here. This is a hypervalent iodine, so it's got, this iodine has more than 4 things on it. It's hypervalent, right? And it, in fact, has a lone pair as well. We're going to see that if we have an alcohol getting involved here, we see that we're going to end up having an attack, and it's going to kick out an acetate. So let's take a look at this. So it's also a mild oxidant, so it will stop at the aldehyde if we're using a primary alcohol. So first step, attack the iodine, kick out one of those acetates. If we do this, let's redraw our molecule. So we have that. We've got our alcohol now. OAC, by the way, acetate. Is that? We're going to see that here. Miss Bailey, what are you doing down there? We're going to have some very interesting sort of things happening here. So we're going to have first our ACO minus. I'm going to grab a proton, giving us the regular thing. This mechanism also is not one you're going to need to know, so don't worry about memorizing it or anything, but we're still going to show the mechanism so that you can see why this is happening. Though I'm sure all of y'all just right now are like, nope, done. Okay, there we go. So we have all our bits here. And I'm going to have to draw one of those hydrogens out. So I'm going to draw the methyl group at the other side. And I should draw this. Sorry, with this one, I have to draw everything kind of nicely and neatly here. So, because we're going to see a whole bunch of arrows are going to come in. So, we're going to have bunch of lone pairs involved with this. So we're going to oxidize our species by grabbing the proton. Those electrons are going to go back onto iodine, which are going to go and reform a carbonyl there. And in doing so, we will have liberated our aldehyde. We lose another acetate. So in this case, we've lost acetic acid, that step. And then we end up with the remnants of our DMP. And so we have now just one acetate group left on there. All right, so it is a big waste of atoms as well. All that stuff there goes away. It's trash. I mean, it can be oxidized later by something else, but it's again not a very efficient in terms of atom economy way of oxidizing. But it is better that we're not using horribly environmentally toxic chromium. So we kind of have the trade-off there. So you either use a environmentally toxic metal, or you use something that has relatively low atom economy. So this one's a little bit better than the Swern, because Swern, the COCl2, the oxalyl chloride, carcinogenic. You of course make carbon monoxide. Dimethyl sulfide is also a toxic gas. So we're making a lot of nasty gases there. Very stinky reaction. Triethylamine also stinks, by the way. All of these things smell so bad. But the DMP is a little bit better. So this is my usual go-to for mild oxidation is using DMP. And so how we might write that is simply DMP makes our aldehyde, or it makes our ketone if we have a secondary alcohol. And then so it's quite simple. So DMP is usually the standard go-to nowadays for mild oxidation of an alcohol. All right. And so if we want to that's kind of it. So it works on primary and secondary alcohols. Remember, your more harsh ones will oxidize it all the way to the carboxylic acid. And but secondaries are okay. You can use your harsher ones on your secondary ones, not a problem. You'll still get a ketone either way. And so it works out either case. All right, but if you want your primary one to not become a carboxylic acid, if you want it to only partially oxidize, you'll have to use DMP, the Swern, or PCC. Either way. All right, PCC, by the way, is not Porterville College, right? I don't know, do I have any Porterville students here? Maybe. So just be aware of that. So, DMP, Des-Martin periodinane. All right, the last thing that we have to talk about is oxidation of phenol, which is interesting. Because phenol, I'm going to draw it with this. Phenol does not have a CH adjacent to it. But we'll see that if we do treat the if we do treat it with chromic acid, i.e. from sodium dichromate, and sulfuric acid, we'll end up with the chromic acid. We see that this one actually oxidizes to the following. We actually will form this quinone. This is phenol, phenyl alcohol phenol, and the following is quinone. And this is super important in biology, forming these quinones. And then if we reduce this, we're going to see that this will pop right back into forming two phenols now. And so it's a way of adding stuff to our benzene. So we can oxidize it to the quinone, and then I'm going to separate these two words. And then we can perform a reduction to get it to go down to the hydroquinone. This is benzoquinone. That's right. And this is hydroquinone. Note this has two more hydrogens in it than the benzoquinone does. And so we just need a reducing agent to do that. And so this works out nicely. All right, so with this, that's just one more kind of oxidation you can do. You can oxidize phenol to benzoquinone, and then you can reduce it to hydroquinone, adding an additional oxygen onto your molecule. So you'll have like kind of really crazily oxidized it with the chromic acid. You have the benzoquinone now, which has many more CO bonds. It has 3 more CO bonds than it had before. And then if you reduce it, you're going to take away one of those CO bonds. And so it's still a reduction. So it's an example that you'll see. This happens in biology all the time. If we look at here, let's bust open biological benzoquinones. Okay, so if we look at some of these sorts of things, let's see if we got some good examples here. Ubiquinone, how about that? Ubiquinone is an important part of biology. Here we go. We see here that if I pop open this window, ubiquinone is biologically part of metabolism. Let me add this window here. So let me just get that window going. So we're going to see ubiquinone is going to be a potent, what's the word? Oxidizing agent. It can oxidize something and be reduced in the meantime. And so we see that in coenzyme Q10. Let's see. Look, you can go get supplements for this. Part of your biological... Oh my god, I'm going to get all these... we're not... Oh, here we go. So, see this Q here? This is part of electron transport, so biological... how we make ATP in our bodies. Our Q here has this oxidation and reduction take place. It goes through the ubiquinone, which is the CoQ10. Let me find a bigger picture. It goes to the CoQ10. You'll reduce it partially and then reduce it an additional time. So you can reduce it fully down to the ubiquinol, which is the benzo or hydroquinone, from the benzoquinone, which is the ubiquinone. So this sort of thing is very biologically relevant, this oxidation and reduction of alcohols and phenols. Super biologically relevant here. All right, so all that stuff still useful for us. All right. So more in biology than we typically. I mean, we see this in chemistry maybe, but it's not so common as it is in biology. So that's it for alcohols. We're done. Exciting stuff. So that'll be it for today. I will put in Canvas some ether videos. I'll post them on Canvas. These will be videos that, again, I recorded at the beginning of the semester for a different class, which has the ether component as part of the second semester. We have it as part of the first semester for some reason, so we'll do that. Don't worry, it's not too complicated. The hardest part is the naming stuff, but that's something we're going to practice anyway. So I'll post those in Canvas. I've graded, I think, maybe a third of the exams so far, so I'll try and finish those later today. By and large, if you had some idea of what you're doing, you did pretty well. Some people didn't show work, and it's like, no work. If you're just giving me a structure, I have no reason to assume it's not a guess, right? And it should be noted on the exam, it was in bold where I said, show all your work. We also did in the review session how to show that work. And then in the syllabus, of course, as well, it says if you want work, or if you want credit, you have to show work. So if you just draw a structure and don't even say, oh, this is a triplet, this is a doublet, yikes. By the way, for what it's worth, I was looking, if you consider MIT, Massachusetts Institute of Technology, very acclaimed. Bailey, what are you working at? You're just up there on the couch. You're not even doing anything. You're just up there on the couch. Let's see if we can see her. She's just there acting as a cat. What are you doing there, Bailey? What was I saying? MIT's NMR actually a little bit easier than mine. Although these were not terribly difficult problems if you didn't fall down a few rabbit holes. A lot of people trusted IR over NMR as well, and that's always a big no-no. I think in the first one, the CH peaks in the IR spectrum, a lot of people thought those might be a primary amine or amide. Primary amide, either way, and you would see the two-pronged blob. But that IR is showing them at 3,000. That's where CH shows up. NH shows up at 3,400, a little bit farther to the left. And really, every molecule will have CH peaks. So, and then in the NMR, of course, you didn't have any hydrogens attached to nitrogen that would show up as an unresolved peak. So. Remember, NMR is always much more valuable than IR is. IR leaves room for interpretation, NMR does not. NMR is a lot more robust of a technique. So that's something I had noticed as well. So I could show you MIT's exam. Is this it here? This is their second semester. Although they have NMR in the second semester. Is it this? Yeah. So this is, let's take a look here just so you can see it. Did I close that window? I didn't. Good. So, my point here is your education is, this is stuff that they do at MIT as well. So you'll have this under your belt. So with the MIT exam, they have, in this case, they give you the NMR spectrum, and they've just given some elemental abundance, so that's how you can figure out the empirical formula, and then go from there. They give you a molecular weight, and then they give you the IR. And look at how easy this is. It's they just give you your integrations. There's your peaks. So you have a septet next to a doublet, 1H6H. All you have is isopropyl groups here. But the you'll see that there's some nitrogens in here. You'll see what this is. I mean, if you want to do this, you can just Google it. And look at this, giving 5 points, 5% of the exam for calculating IHD. What a joke! So you guys are doing more work here, which is nice. So, like, what structural fragment? Of course, that's an isopropyl group. The second one, again, 6H singlet. They give you the coupling constants for these, as well as the carbon NMR here. It's pretty fun. So, then some random problems. So, there's by the way, they have an hour to do this, and they're talking about, you know, some conceptual stuff like we had, and then you've got your spectrum interpretation. So so good. So it's fun stuff. So if you want, you can go and find, if you just like Google MIT exams or something, you can find some of these. This is OChem 2 because that's where they do it. That's where they do the spectroscopy. We do it in OChem 1 here, but it's just more resources, right? So you can see the stuff that they're doing. Look at these poor students, by the way, who had to do like, no, this is not the one I wanted to show you. Was it exam 2 maybe, or practice exam 3? Yeah, look at this. They have to do fill in all this stuff. Oh no, this isn't the one I wanted either. Practice exam 2 maybe. Yeah. They had to do A through X for predicting the products. How crazy is that? And they have 1 hour to do all this stuff. 72 points, A through X, predicting products of things. These are all Diels-Alders, something we'll cover next semester. It's kind of ridiculous. So they have 50 minutes to do all of these problems. So this is what's expected. This is normal for OChem. So in case you're thinking like, oh my god, I can't do this, like what is happening, it's like this everywhere. And in fact, you'll get more in-depth problems with me than with some of these MIT ones. You'll see, if you look at those as practice, they're very basic questions. Mine tend to be a little bit more involved. And there are other instructors I know who are way more involved, use way more complicated structures than I do. So I'm kind of in the middle here. So suffice it to say, you're getting a good education. This is normal. So you will be well prepared for the ACS exam in this course. So ACS is a standard exam. It's administered all over the country. And so with this, you will be very well prepared. So, okay. So that's it for new material for this course, aside from those couple of videos I'm going to post on Canvas that I will have you watch. So on Wednesday, let me know what time you'd like to review, what questions you have, and we'll go from there. So let's hope you're watching this so that you'll know this information. All right. Awesome, then. Take care. We'll see you on Wednesday at whatever time we like. We'll do it in Discord, and we'll go from there. All right. Take care.